Hi, um, welcome. I'm Narendra Mukherjee. I am a machine learning scientist at TripAdvisor, and I'll talk to you today about missing values in model features and how that's a problem in real world ML systems, and how we can use Bayesian inference to get around this problem. So, to start off, a few things about myself. I am a machine learning scientist in TripAdvisor's B2C data science team. I have worked in a variety of domains in the company, which range from sort and recommendations to NLP and a few other things. Previously, before I started at TripAdvisor, I finished my PhD in neuroscience from Brandeis University, which is in the Boston area. I I studied taste processing in the brain during my PhD. I am a long-time Bayesian enthusiast, and I have used a lot of Bayesian inference in my research work during my PhD, and continue to do so in the work I'm doing at TripAdvisor. I am also a passionate cyclist. In the years that I have been in Boston, I've cycled more than 10,000 miles in the area. And to know more about myself, please do go to my website, where you will also find the slides from this talk in my blog. About TripAdvisor itself, if you're not familiar with the company, TripAdvisor is one of the world's largest travel-related websites. It is a one-stop shop for everything to do with travel, ranging from hotels to things to do, to restaurants, to flights, everything that you can think about. It also has a lot of travel forums where there is a lot of user-generated content, including reviews for different sorts of attractions, locations across the world, reviews for hotels, for flights, anything you can think about. And the motto of the company is to find the good out there, which is to help you plan the greatest trip of your life in the same place. And so, as you can understand, for a travel-related website like ours, the product sort is a very essential feature for a smooth user experience. So, by products, we could be sorting many different kinds of things on the TripAdvisor website. So, one of the things we could be sorting are tours and tickets. Like in Amsterdam, we could have a canal cruise or a museum ticket, and or a bus tour, and we want to sort all of those. Or we could be sorting different sorts of hotels. We could be sorting vacation rentals. We could have sorts for restaurants, flights, and all the other different domains that the company works in. And all of these are really important, both from the user experience perspective as well as from the perspective of the company, which is trying to sell products. And so the story today will focus on sorting at TripAdvisor. Specifically, it will focus on sorting lists of products in TripAdvisor's experiences business. And experiences means tours and tickets, which is basically museum tickets, hop-on, hop-off tours, guided multi-day tours, things like that. And to do this task, we use many different kinds of features, which could include product-specific features like price, star rating, click-through rate, conversion rate, stuff like that. We could have user-specific features like the user's prior browsing history, their geolocation. We could have other features like seasonality, time trends. All of this we can use to predict the probability that the user will click on the product or book on the product, and then we sort products based on that probability. To be able to deal with features of so many different kinds, we usually use gradient boosted trees, which a lot of you might be familiar with. So algorithms like XGBoost or LightGPM, and these are great at capturing interactions between such a wide diversity of features. The problem that we will be talking about is that of missing values in model features. So basically we have a bunch of different features in the model, and we might not have values for them for individual products or users. So to be able to understand the problem better, understand its magnitude better, there are two specific questions that we will talk about. The first is, how do missing values arise in a sorting task? How do we start to have missing values in the first place? And the second one is the why question, as to why does having missing value hurt performance in a sorting task? And we'll get into the details of both of these questions in the next few slides. So to address how we get missing values in the first place in a sorting task, let's take an example of a sorting task. So there are 4 products that we are looking at over here. So let's look at the first one. I call that Old Faithful, and that product has been there on our platform, say, for a few years. It's a popular product. It's not that expensive. It's $20 or so. It could be a museum ticket, like anyone who goes to Paris gets a ticket to the Louvre, for instance. And so it has a lot of views, a lot of bookings. It has a high conversion rate, lots of reviews and ratings. So we know a lot about this product because it's been on the platform for a long time. And so this is unlikely to have missing values in its features. Similarly, we have a different product which has a lot of views and has been on the platform for a long time, but this product is more expensive. It is, in this example, it costs $200. So it's not booked as often as the Old Faithful product, but still we know the conversion rate of this product. We know the number of reviews, the star rating for this product very well, because it's been there on the platform for a long time. But now we could have a new product on the platform which has been there, say, maybe for the last couple of weeks. It has had a few views, it has had a few bookings, but it doesn't yet have any reviews and ratings on the platform. And so if we use this product, if we had to sort this product in a list of products, we would have missing values arising because this product has not been around on the platform for a while. On the other extreme, you can have products that have been available on the platform for a long time, but they are out of season. So imagine a place like Boston, which gets very cold in the winter, and think of a sailing cruise in Boston in December. So if you look at the sailing cruise in December, it's probably not been viewed or booked for the last month or so. It does have a lot of reviews and ratings because it does get booked in the summer, but it is out of season in the winter. And so if we are trying to sort this product in the winter, we have a bunch of missing values because it's not been viewed or booked in the past few days that we might be looking at. So these are a couple of examples by which we can have missing values arising on our platform. But an even more common and pervasive situation in which missing values arise is if you also take into account the user's intent or user-related features when you are sorting products. So let's look at these 2 products over here. The one on the left is a snorkeling tour. Cost is $65. It's viewed 5,000 times, booked a bunch of times, so it has a high conversion rate. The one on the right is also viewed a similar number of times as the one on the left, but it is much more expensive. It's $560. It's a private yacht rental. It's not booked as often, probably because it's expensive, and it has a low conversion rate. Now, if we were designing a recommender system and serving recommendations to a user, we would probably put the product on the left at a higher position than the product on the right, because the user is more likely to engage with the product on the left. It's better for the user experience. It's better for the company as well. But what if I told you that out of the 5,000 products for the yacht rental, only 100 were from users who explicitly selected a yacht rentals filter? So in that case, what would be the right value for the conversion rate of that product? Should we be considering all the views of the product, or should we be considering only the views where the user explicitly expressed intent to buy a yacht rental? So should the conversion rate be 0.01 or 0.5 if you divide it by 100? In addition, the question gets even more interesting if I tell you that the list is being served to a user who has selected the yacht rentals filter. In that case, we should probably be presenting the product on the right at a higher place than the product on the left, because then the user is probably not interested in a snorkeling tour. So it's important to take into account all of these different filters that the user can select on the website as they are looking at products. But that's where the problem arises, because we don't have conversion rate or click-through rate for each product for every filter that we have on the website, because not all products are viewed with all the different types of filters that can be there on the website. So you can have a lot of missing values if you are featuring in user intent into the model as well. So there's a lot of different scenarios in which missing values arise. So now that we understand how that happens, let's get into why missing values hurt performance in a sorting task. And that's the more important question. So how this happens is that training data in the sorting task, or actually in any other machine learning task that's built on sort of user behavior on the website, the training data is built using user impressions or views. So you only have the products or filters in your training data set which the users have looked at. So many products or filters that the users don't use that often on the website might be missing from the training data, and that is fine. That's okay if the data you are trying to predict on is also of a similar nature as the training data. But what happens in a sorting and recommendation system is that you have to serve recommendations to every user who might come to the website, every possible user that might come to the website, and you have to sort every single product that is there on your platform. And so the model has to serve predictions for all combinations of product user features, and many of those might be missing from our data. And so the model encounters a lot more missing values at prediction time than it is used to at training time. And the model has to extrapolate beyond the training data. And those of you who are experienced with tree-based models understand that the word extrapolation in this context means disaster. So tree-based models cannot extrapolate beyond the training data. Given they make splits based on the different training instances, they usually make constant predictions out of the regime of the training data. So they are really bad at extrapolating, and this is a huge problem. And in addition, I would argue that this is an even bigger problem in the case of the sorting task, because from the business perspective, the sorting task is extremely visible, and bad predictions in a list of recommendations are extremely visible. It's not like the other machine learning tasks that you might do in a company like ours, like say predicting auction revenue or something like that, where it might be enough to do well on average, as in any other machine learning task. It might be enough to have a good mean squared error, for instance. But here, you might have a good mean squared error, but for instance, if in a popular location like Paris, you put up a bad product in the first position in the list, it's very bad for user experience. It's very bad for the commerce on the of the company. And so individual recommendations matter a lot in this sort of a task, and so missing values become even more important. They hurt performance even more in this sort of a situation. So I hope that I have motivated you enough to understand the source of missing values and the problems they cause. But how might we go about dealing with them? So you might have already come up with a bunch of recommendations of how to deal with missing values, and one of those could be to drop all rows which have missing values. So what happens is in our use case, or actually in any real world use case, when you have a bunch of features in your model, and all of them are missing values for different rows, if you ended up dropping all the rows which had any missing values, you would probably not be left with any rows at all. In our own data set, you would hardly be left with any rows enough to train a model. So this does not work at all in any real world scenario. The other thing that people commonly do is to replace missing values with each feature's mean, and that's a common thing that is done. But this is not a good idea when a feature is missing a large percentage of values, which is often the case for many of our product filter combinations, as I was talking about. If a high percentage of rows for a particular feature are missing values, then the mean of that feature is dominated by the extreme values. So, for instance, if we are imputing conversion rate, the imputed value for the conversion rate would depend the most on the products which have the highest conversion rate, and that's not really representative of the population conversion rate, so to speak. So that's also not a good idea. In addition, replacing missing values with each feature's mean neglects any sort of interaction that the features might have between each other, and so we don't take that into account as well. We could also let the XGBoost or LightGBM algorithm handle missing values on its own, and it is able to do that natively. But that's often not a good idea when almost all features in the data set have some number of missing values, because what gradient boosting algorithms do is to make the best split on average when they hit a feature which has missing values. But this split does not depend upon any of the previous splits that the algorithm might have made in the tree. So this is not the most optimal split they would make if you take the whole tree into consideration. So this is not usually a good idea, and you can read this Housing Anywhere blog post to get more details on this problem, for instance. And finally, one of the things that is often done to deal with all of these issues is to use k nearest neighbors imputation of missing values. So you use some predefined k values to impute the missing values in our data set. And while this is a good idea, it deals with many of the problems that I've talked about in the previous the 3 points, but it is not something that is scalable. It's k nearest neighbor finding is impractical in a recommendation system, because we have strict latency requirements. We need a list of recommendations to be served within milliseconds to keep the web page responsive. And you can read more on the Airbnb blog post I have linked to here to get an idea of how k nearest neighbors is done in such a situation. So anyways, none of these methods really works for our specific use case. So what did we use eventually? So what we used is scikit-learn's iterative imputer. And what this does is a sort of round robin imputation of the features. So you impute the features one by one based on the values for all the other features in the data set. So what this means is an algorithm something like this, where you start with an initial imputation of the missing values in each of the features by, say, their means, for instance, some initial value that you want to impute with. And then you loop through the features, you pick a feature I, and then you build a model, a predictive model for the values of that feature which are not missing, using the values of all the other features in the data set. So this can be any sort of predictive model F that you can think about. It can be a tree, it can be linear regression, it can be logistic regression, whatever you want. And then you use this predictive model to fill in the missing values for feature I using, again, the other features in the model, all the other features in the model. And then you loop through I in this way. And you keep doing this till you hit a tolerance limit. So you basically go through features one by one, fill in each one based on a predictive model defined on the basis of all the other features, and you keep doing this till the missing values don't change anymore. And so this strategy achieves a couple of the different objectives. One is that it takes into account the relationship between the different features, because the predictive model F is explicitly built based on the other features, the minus I features in the data set, and only k nearest neighbors is able to do this. But in contrast to k nearest neighbors, this provides a predictive model F that can just fill in the missing values at prediction time. So you don't have to search for k nearest neighbors at at prediction time, you can just use F to fill in the missing values and then run your model on top of that. And this does not add much latency to the prediction process, and that's exactly what we need. And so it worked very well for our purposes. To show you an example of how this works in our sort and recommendation system at TripAdvisor, and in addition, as I was saying, the user can modify both F and tolerance to trade off between imputation speed and quality in this setup. So we ended up using the default values that are provided as part of the iterative imputer, and that worked pretty well for our purposes. So as I was saying, I wanted to give you an example of how this works in our particular setup. And so let's look at an example experiences sought from TripAdvisor. And we started off using a naive approach where we would replace the missing values for the click-through rate or conversion rate of every product filter combination by -1. So the logic behind this was, if we don't have the click-through rate or conversion rate for a product, that product has a click-through rate or conversion rate which is lower than the minimum possible value, and the minimum value is 0. So we just replaced it by -1. And usually this happens with the number of views is 0 for this product filter combination. As I have shown you already in a previous example, that's something we realized in hindsight. The number of views can be 0 even for very popular products if they have not been viewed in a particular filter combination, for instance. So this, even at the start, doesn't seem like a good idea, but we tried it initially when we did not realize this. And this is what happened. So these are the top 5 products for one of the experiences pages in London. London is one of the most popular locations on the website. And we see a bunch of different products. We see at the Tower of London entrance ticket. We see a Christmas lights tour of London. We see a Stonehenge tour. And we see a hop on hop off tour. So these 4 products, all of them have a pretty high number of views, high number of bookings, a good conversion rate. And so these should be at the top of the list. But in the 4th position over here, we also get a private walking tour of London with a Portuguese speaking guide, which has 0 views, 0 bookings, and our imputed value of -1 for the conversion rate. And actually, surprisingly, when we went and did a SHAP analysis of this model, we saw that this product's predicted score is driven up precisely because of these 0 values and the -1 value for the conversion rate. So our imputed value is actually unnaturally driving up the predicted score for a product that has no views on the platform, and this is not good behavior. This is unexpected behavior from the model, and initially we were concerned about the model itself before we realized the missing value issue. And when we replaced our naive approach with a more principled approach, where we impute missing values using the iterative imputer, we see that the 4 good products from the previous page, the Tower of London ticket, Christmas lights tour, the Stonehenge tour, and the hop on hop off tour, persist, but the private walking tour is now replaced by a different tour which has a high number of views and bookings and CVR as well. And so this is a much better sort that we get as a result of imputing missing values in a more principled manner. So the take home message from all of this is that missing value imputation is especially important in a sort related task, and especially if we are using a tree based model to do it. And often missing values can be the culprit for any bad performance that we see from the model rather than the structure of the model itself. So it's important to think about them. So now I will make a major change of gears and ask the question of how and why does the iterative imputer work. Initially, when I started working with this, it seemed like a mystery to me that this round robin imputation should work. But if you think of it from the Bayesian inference perspective, I realized over time, if you think of it from a Bayesian perspective, it makes more sense. And so we will discuss that for a few minutes. So to start off, I want you to think of a probabilistic graphical model, which has products over here from 1 to n, which are along the rows. And each product has D features, which go from 1 to D, which are along the columns over here. And some of these features are missing at random for the different products, and these are labeled by M. The missing values are labeled by M. And so we can think of this as a probabilistic graph where the filled in observed values are the ones that are filled in over here. The missing values are the latent variables, unseen variables of this probabilistic graph, and we can do inference in this graph. So now we can take two extreme views of imputation. We can make two extreme views of the structure of this graph itself. So one extreme is to keep it really simple and to forget about any of these links between the different features of the different products. So you get rid of all of these links and model each feature as an independent Gaussian. And so we would then replace the missing values by the MLE, which would be the sample mean. And so any sort of mean imputation is, from a Bayesian perspective, doing that. It is ignoring any sort of relationship between the features. Or we could go to the other extreme where we model every single relationship between the features of every single product. So we model the entire joint distribution of all the features of all the products, and this would be called joint modeling in statistics. And this is a very hard thing to do. It can only be done under restrictive assumptions. So these are the two extremes, and as you can probably guess, I'm trying to take us to a situation where we strike a good middle path between these two extremes. So let's think of the full joint distribution, which is the probability distribution over the missing values, the observed values, and the features taken together. And then think about what we want to do. We want to model the posterior distribution of what we don't know, which are the missing values, which are the latent variables in this model as well, given what we do know, which is the observed values. So the posterior over the missing values given the observed is proportional to the likelihood of the observed given the missing and features, and a prior over the missing values. And this is just Bayes' rule in action over here. And as you can see, we can apply the full machinery of Bayesian inference to this problem, to this sort of conditionally independent sort of distribution to do posterior inference in this problem. So obviously, one of the things you can do when you're doing Bayesian inference is to do posterior inference using MCMC and PyMC3, which is the biggest MCMC package in Python, by default performs posterior inference over any missing values in the input data set. And I would encourage you to get more information on this at this upcoming tutorial at PyMCCon, which will talk about more details on this. And for those of you who are more familiar with MCMC sampling, you would realize that this task becomes even easier if we can sample from the conditional distributions of the features. So these distributions, the probability of each of the features, the probability of feature I given all the other features, if we can sample from those conditional distributions, then this gives us a pretty easy Gibbs sampling scheme to sample from and do inference in this graph. The other thing which you can do, which is usually faster than doing MCMC, is to do approximate Bayesian inference. So again, let's assume that we have some sort of understanding of the conditional distribution of each feature dependent on every other feature, and I'm calling that Fi over here. So that's the probabilistic relationship which describes feature I in terms of all the other features in the model. And if we have this conditional relationship, this is ideal for an expectation maximization or EM recipe. So you cycle between optimizing the parameters of the conditional distributions Fi. So it could be the mean and variance of these conditional distributions that you are trying to optimize, and the latent variables, the missing values M themselves. And that's a very standard EM approach to do this. And there can be many different flavors of doing EM in such a graph. And as you know, in addition, that EM is guaranteed to find a local maximum of the posterior. If it's done iteratively in this fashion. So there could be many different flavors of EM in this sort of a graphical model. Firstly, we could be doing variational inference, which I'm calling fully Bayesian here, because we are maintaining in variational inference, we are maintaining probability distributions over the parameters of the FI, as well as we are maintaining probability distributions over the latent variables M as well at every iteration. And then we average all estimates of interest with respect to these conditional probability distributions. So that's what variational inference does. But you could also do a simpler scheme, which is what I would call a standard EM, which is partially Bayesian, where you maintain conditional probability distributions only for the latent variables, so only for the missing values, but not for the parameters of the FI. So you estimate the mean and variance of each FI exactly, but you don't estimate the latent variables exactly. You maintain posterior distributions over them. And an example of this, where in a different situation, would be the Gaussian mixture model, where the means and variances of the mixture component themselves are the parameters. Those are the parameters of Fi that I'm talking about, and the membership of each of the data points in each of these mixture components are the unknown latent variables, the equivalent to the missing values in our probabilistic graph. And finally, we could have an even simpler scheme, which in the machine learning literature is called iterated conditional modes, or ICM, where we set all the random variables in our graph, so both the parameters of the FI as well as the latent variables, to their map or MLE estimate at each iteration. So no distributions are maintained at all through the iterations. And this is a really fast way of doing approximate inference. Obviously, as you can understand, you get greater detail by maintaining the distributions, but you gain on speed if you don't. And an example of this would be k-means clustering, where unlike Gaussian mixture modeling, you don't maintain the posterior over the cluster memberships in this situation. You assign points to clusters directly. So with that in mind, if we go back and think about the iterative imputer itself, it is doing ICM in the probabilistic graph of missing values that I showed you at the start. So to understand this, let's look at the algorithm, the iterative imputer algorithm that we looked at a few slides ago. And here's the algorithm. And let's examine its steps again. So for instance, the first step of initial imputation of missing values by the means of the feature can be thought of as setting a prior over the missing values. That's something you need to do in an EM setup anyways. And then each of these iterations in the imputation process consists of an M step, and the M step is when you're training this predictive model for feature I given the other features. So these are this is the step where you are getting the parameters, the means and variances of the FI that I was talking about. So that's the M step, and then you have an E step, which is a hard E step here, because you are directly assigning to the missing values the maximum likelihood values that are predicted by the FIs themselves, by the predictive model that we trained at the previous step. And you keep doing this till you hit a tolerance the tolerance limit, again, as you do in standard EM procedures. So that gave me a much better understanding of this imputation process, and that explains why the iterative imputer is able to come up with good imputations, because it is just doing a standard EM sort of inference in a probabilistic graph. So finally, before Oh yeah. Before I get there, this model is also known in the statistics community as multiple imputation with chained equations, and I urge you to look more at these two links to get more details on that. But it was good for me to get a machine learning Bayesian inference sort of understanding of the process as well. Um, I, I'll just end with a word of caution in that ICM can get stuck in local optima, as with any EM strategy, and that's why, which is as again is a standard in EM, you need multiple random restarts. And in the machine learning community, usually it's okay to just pick the best fit amongst the multiple runs as the one fit we will look at and we'll feed into our later models. In statistics, the different restarts are used to get confidence intervals on the estimates. It's used kind of like a bootstrap estimate. And we in our use case got reasonably good results in the missing value imputation problem with even just one restart, with just one run of this model. So with that, I'll finish my talk. I urge you to come to the Q&A sessions, and I'm hoping to see you there. I expect questions there, and I thank you for your time. Please do visit my website to get more info about the work I do and to see the slides for this talk. And thanks a lot.